We now want to look at an application of differentiation, and that's going to be exponential growth and exponential decay. There are lots of things that either grow or decay or increase or decline exponentially. In other words, with, for example, a population, has often been found that populations grow at a rate that is directly proportional to the current population. Now, if you have forgotten something about proportionalities, when you say something's directly proportional, that means that the output is equal to a constant times the input. In other words, a direct proportionality is a situation in which you have a linear equation that passes through the origin. There's plenty of examples of direct proportionality. For example, the circumference of a circle. Circumference equals 2 pi times radius. So in this particular example, the circumference is the output, the 2 pi is the constant, radius is the input. All right, so again, if you're in a situation where either the growth or the decay is directly proportional to the current population, then you're dealing with exponential growth, or if it's going down instead, you're dealing with exponential decay. Now, therefore, since it's not the current value that's directly proportional, it is the growth or the decline, it is the rate of change, then the equation is no longer y equal k times x. The equation is dy dt, which again expresses rate of change at any particular time, equal to a constant times not an x, but a y, because again, as we said, the rate of change is directly proportional, k times the current amount, the current population. In this scenario, if k is positive, you have growth, because that means that the rate of change, the slope, is positive. If k is negative, then you have decay, which means the rate of change is negative. The population is going down. And again, this can be applied to human populations, the number of bacteria in a petri dish. This can be used for as money as well. There are plenty of monetary examples that go with this. I'm not really interested in the monetary side, but again, if you have continuously compounded interest, then it obeys this rule as well. This rule is often called the law of natural growth when A is positive, or the law of natural decay when it's negative. Now, in a differential equations course, there are theorems that you can prove or see proofs of that are called uniqueness and existence theorems. Theorems that basically say for an equation like this, a solution exists. This is the solution and it's the only one. All right, now that is, of course, beyond the scope of what we're doing here, so I will just state the theorem. The theorem says that the function that obeys this, that models this behavior, is y of t, meaning population at time t, equaling y0 times e to the kt. In other words, the theorems basically say the only function that fits this pattern is here. The one that says population at time t is equal to y of 0, which would mean initial population times e to the kt. Notice that if we take the derivative of this function, to sort of observe one thing, we take the derivative of this function, we get a y0. Again, this is a constant, so it just sits up front. Derivative of an exponential will be the exponential times, chain rule says, take the derivative of the exponent, and from that you get a k. Rearranging this slightly, I'm going to take the k and toss it out front. Notice that the derivative of the original function is equal to k times this. And what is this? Hopefully you recognize it. It's the original function. So notice that this function does fit this pattern. The only thing I really can't prove to you right now, again, because it's beyond the scope of this course, is that this is the only one that works. For that, you'll have to wait for a differential equation class, and you'll be able to prove, like we did, that this function satisfies this requirement, and you'll be able to go on to prove that it's the only one that satisfies that requirement. All right, so what kind of example, what kind of application can we put this to use with? Let's say that we know that the world population, okay, the population was equal to 2,560 million people in the year 1950. And the population was equal to 3,040 million in the year 1960. So we want to try and use this to model the population of the world in the second half of the 20th century. Right? So some assumptions or some assurances have to be made. We're going to assume that the growth rate is proportional to the population size. In other words, what we're saying when they make that statement that growth rate is proportional to population size, they're saying that this can be modeled with the exponential growth function. Now, I use y's for my function. Typically, they're going to use p's if we're talking specifically about a population. So the statement they've made has told me that population at time t, they have assured me, can be modeled by initial population times e to the kt power. Now, the way this is typically done is we pick a year that's going to be year 0, and in this case, it would be appropriate for 1950 to be quote unquote year 0. All right. So therefore, my model, I can refine it further to say population at time t is equal to the initial population. And since our little experiment starting in 1950, the initial population is 2,560, and we're writing this all in millions, times an e to the kt. All right. In addition, we can use this value for this year to say that the 2,560 e to the k times 10, because they're looking at 10 years later, is equal to a 30, 40, and again, everything's in millions. So what I need to get from this, what's still missing, is that k value. So I would divide both sides by the 2,560. And then to solve for k, I'm going to take the natural log of both sides. Natural log and e are inverses, so I get a 10k equaling the natural log of the 30, 40 over 2,560. And finally, k will be the natural log of 30, 40 over 2,560, all divided by 10. And for this situation, since it is truly an application, I think a decimal would be appropriate. So I'm going to take the natural log, 3040 divided by 2,560, close parentheses, divide that answer by 10, and I get a 0.017. And I think 4 decimal places ought to be enough. Okay. In many scenarios, this would be referred to as a 1.72% exponential growth rate. All right, just so you know that that is a term, that is a language that is used. What I can do with that is go back and further refine my function and rewrite it as 2,560 e to the 0.0172 t. So I've got my k figured out. What can you do with that function? Well, a lot. If they said, what would you estimate what the population to be in the year, say, 2000? Well, the year 2000 is 50 years later, so I'd put in a 50. And calculate. So I'm going to have a 2560 e to the power 0.0172 times a 50. And from that, I get a 60, 40, and might as well call it, might as well round it off, 250, 60, 50. And then again, remember, everything's being done in millions. All right. So that's what the equation could be used for, is to predict future amounts. Or if they wanted to, they could say, when would the population reach, when is the population, which the population function, when is it equal to that number, 7,000 millions. And again, from that, you could divide both sides, take a natural log, and you could solve for t this time instead of k. But the procedure that I used to solve for k is identical to the one you would use to solve for that t. With a radioactive decay problem, you're going to use the same function, same type of function. All right. For example, if they were to say the half-life of radium-262 is 1,590 years, and you take a sample and you want to know the formula after so many years, again, as long as you know, as long as you are assured that it follows the same kind of pattern, you therefore know what type of function can be used. And again, when you're talking about the radioactive decay of a substance, they're talking about mass. So instead of a Y or a P, they'll use an M. So we'll know that mass at any time t is equal to the initial mass times an e to the kt. And if they tell you that the half-life is equal to 1,590 years, all right, as it turns out, we don't have to know the original amount to be able to work this particular problem, all right? At least get the equation set up. So if they tell you the half-life is 1,590 years, you can say that the mass at time 0 times e to the kt is equal to 1/2 the mass at time 0, because the mass has been cut in half, times an e to the, let's see, the 1,590. Oh, hold on. I can do this better. I can make this a little bit easier. Okay. Here's an easier approach. If you just say mass at time 0, e to the k times, let's go ahead and put the 1590 in here. Let's put it on this side instead, equal 1/2 mass at time 0. There we go. That's cleaner. All right. Mass at time 0 times e to the k times 1590. So I've just plugged the time in with 1,590 years. And that should come out to be equal to 1/2 the original mass. Now at this point, you can divide both sides by m naught, and you'll see that it cancels. So what you discover is that the original mass really isn't relative to this part of the problem. So we have an e to the 1590k equaling a 1/2. Natural log both sides. 1590k equals natural log of 1/2. K is natural log of 1/2 over 1590. And again, for problems like this, it's probably appropriate to go with a decimal. So I'm going to take the natural log of 1/2, divide that by 1590, and I get a negative 0.000436, basically. The number came out negative simply because it is a decay problem. Things are going downward, and therefore my mass at time t, it will now be equal to initial mass times e to the negative 0.000436 436 T. Now, if they were to go on to say, oh, we have a sample of mass 100, what's the formula for it? Well, for this substance, if your initial mass was 100, you just plug in 100 in, and you have the formula that will tell you your mass at any particular time. Mass after 1,000 years, a mass after 10,000 years. This will work for you. Okay, this will do that type of problem for you. Something else that we will deal with in an application setting are things that are either heating up or cooling down. The next law is called Newton's law of cooling, but it works also for things that are heating. It doesn't really change much if something's heating up versus cooling down. Newton's law of cooling, just by experimentation and observation, it was found that the rate at which something cools is proportional to the difference in temperature between the object and its surroundings. If that sounds familiar, it should. That's saying that the change in temperature with respect to time is directly proportional to the difference between the current temperature and the temperature of an object's surroundings. All right. Now, the problem is I can't use the same formula I've used before because there was not a difference. There was no subtraction in that earlier formula. All right. So what we want is a function that will tell us temperature at any time. But what we're going to have to do is settle for, at least for the moment, a function that gives us difference in temperature. In other words, if we let y of t, I'm not going to make up a dummy variable, I'm going to make up an actual dummy function. But we're going to let y of t be temperature at any time, temperature at any time, minus temperature of surroundings, then this formula becomes dy dt equaling k times y. And this does fit, all right? This does fit the pattern, the formula that we saw before. So again, remember, function t, function capital T, is the temperature at any time function, whereas function y is the difference in temperature function, all right? So what we know, again, from the theorem earlier, that means that y of t, difference in temperature at any time, is equal to y at 0, meaning initial difference in temperature, times an e to the kt. All right? But from this, what we can actually do, since this was the function we actually originally wanted, if I know that y is a difference in temperature function, then if I just add back, all right, again, with y being temperature times t minus temperature surroundings, if you just add temperature of surroundings back, you get temperature at time t. So I can take this and make the next logical step. And if I have just initial difference of in temperature times e to the kt plus the temperature of the surroundings, then I have a function that will work for temperature at any time. All right, so for example, if they said a bottle of soda pop at room temperature, so that means the temperature at time 0 is 72 degrees, is placed in a refrigerator where the temperature is 44 degrees. Well, if the refrigerator has a temperature of 44, that's the temperature of your surroundings. If the bottle of soda pop has an initial temperature at initial temperature 72, then the initial difference in temperature is going to be the 72 minus the 44, which is a 28. Therefore, my temperature at any time t is going to be the initial difference, which was 28, times an e to the kt, which I haven't figured out the k yet, all right, plus the 44. All right, so again, in this function, temperature at time t is going to be equal to initial difference times e to the kt plus temperature of surroundings. Only thing I'm missing is the k. So if they were to tell me that something like that the temperature half an hour later is 61 degrees, so in 30 minutes, temperature is equal to 61 degrees, all right? What I can do is go back to my function and say, well, okay, temperature at time 30 is equal to a 28 e to the 30k plus 44, and that's a 61. What I can do is move the 44 to the other side by subtracting. So 61, take over the 44 is a 17. All right. And now divide by the 28. And 17 divided by 28 would give, let's keep it 17 over 28. That's ugly. Natural log, both sides. And divide off the 30, and you've got your K value. And you finally have the K. All right, you can put that back into your function. That means now that temperature at any time t is equal to the 28 e to the power natural log of 17 over 28 all over 30t. I know it's an ugly number, plus 44. And with that function, you can predict the temperature at any requested time.